1, go.
Hi, everyone. I'm going to be presenting Chapter 4 on classification methods from the Introduction to Statistical Learning with Applications in Python book. We can go ahead and start with what is classification. Basically, classification is predicting a qualitative response for an observation. Can be referred to as classifying that observation since it involves assigning it to a category or class. I got my notes. Previously in linear regression, it was used for predicting quantitative variables. And these classification methods are for predicting categorical or qualitative variables. I'm probably going to mostly use the word categorical. Qualitative in my day-to-day is like interviews and focus groups, so it's confusing to me. So I'm going to use the word categorical probably. Don't hold me to it. Some questions. The Reveal.js preview got me, so some of my margins aren't perfect, but you can see most of it. Some questions that we can solve with classification are triaging emergency room based on symptoms, and then an online banking service must be able to determine whether or not transaction being performed is fraudulent or not. Some hypotheticals I came up from my own work in program evaluation. Truthfully, these would be really unrealistic to like actually implement, but predicting whether or not a participant in a professional development program completes the program or not, and then predicting whether or not like a family returns to an annual family camp weekend program in the next year. Those are some of the things that like I might have used classification methods in my work, but again, it would have been not realistic to do so. A lot of this chapter is like, why not linear regression and why should we not do the method that we just learned about? So there's gonna be a lot of like, why not this? Linear regression shouldn't be used to predict categorical variables with more than 2 levels that don't have a natural ordering like stage 1, stage 2, stage 3, or a reasonably similar gap between each level. You could recode a binary variable to 0, 1, but you most likely end up with negative probabilities, which tend to not be very meaningful. And there are some extra images in the book version of the notes. If they're like missing some of the graphics, those will be in the notes once it's all merged. In those cases, that linear regression won't work. Logistic regression can sometimes be a good option. In logistic regression, we're modeling the probability that the response belongs to a particular category instead of modeling a quantitative response directly. In this image, on the left, you can see the default data set. The default data set has like a binary variable called default. That's yes or no, whether someone would default on their credit card payment. And then it has some like other variables that we'll use later in the chapter for prediction. And on the left, you can see it with the linear regression. And on the bottom left of the chart, you can see if someone has a balance of 0 on their credit card payment, the probability of default is negative, which just doesn't really make sense. It isn't very meaningful. On the right is an example of the logistic regression. It will always have that S-shaped curve, and the probabilities will never reach 1 but become very close, and they'll never reach 0 but they'll become very close. And so you can see that any value of X can be used to predict the probability of Y falling into either of the categories. Changing my notes around. The Introduction to Statistical Learning in our book, the book club has a lot of the LaTeX and functions, so thank you to that person, those people who have contributed to their book because their LaTeX was really helpful. And if there's any other notes that anyone's missing from this chapter, there might be additional context in that book. Some comparisons between the linear regression and the logistic regression. Beta 1 in linear regression is the average change in y associated with a 1 unit increase in x. But in a logistic regression model, increasing x by 1 unit changes the log odds of beta 1. And you can see the functions here. Yeah. The maximum likelihood method is used to estimate the regression coefficients, basically so that the coefficients are chosen based on the probability estimates being as close as possible to the observed response of y for each case in the training data. And then I found it really helpful to see like actual values put into the formula. And so this is an example from the book. I had to take out the table that showed the coefficients, but they're here as like the -10 and the 0.0055. And then with a value of X for bank balance or credit card balance, the prediction of default is 0.00576. And then you can also add in order to get to multiple logistic regression, add in multiple predictors to the formula. And then there was just some cautions against only using one predictor when many may be relevant. And their example was taking into account whether or not students were taken into account in the model. And this is known as confounding. And so someone who's a student is less likely to default than someone who is not a student with the exact same income and credit card balance. And then multinomial logistic regression. I didn't include the formula. I didn't include the formula here, and I'm not going to go too much into it. Besides what's here on the screen, is there anything that anyone want to discuss about the multinomial logistic regression? If any of you have gotten to it yet?
I maybe just, the last slide about the student. I thought what it was saying in the book was pretty interesting. Well, not pretty interesting, but like quite funny, like because it was saying the students are like more likely to default overall. But if you take two students, or like a student and a non-student, and you give them the same like credit card balance and whatnot, then the student will be less likely to default, which was like quite an interesting thing. And I didn't actually sit and think about it loads, but I was wondering, what, say if you found that, what would people try to like understand about students to explain that? Or what kind of explanation would you want to come up with, or could you come up with for why that might be the case? And that's just like an open question.
But we don't know. We don't know if there is not bias because not all students can get the credit card. So we don't know that. So maybe the filtering was before.
Yeah, the students who won't default or less likely to default were approved for the credit card.
Yeah.
Yeah, I haven't looked at the data set, but does what's the imbalance in? I hadn't actually thought of that, which is good. What's the imbalance in number of people who are a student versus number of people who are not a student? But I mean, the other obvious thing is students are likely to have a lower cap on their credit card, I would say. And it's kind of the higher your credit card balance, the more likely you are to default.
And don't forget that the purpose of the credit company is to have a good model to know to whom they have to give the credit card and which balance. So basically, if they have a good model, they shouldn't give the credit card to somebody who is going to default.
This will apply equally to the students and non-students, right? So if I think,
is my mic not working?
yeah, no, it's on.
Sorry, I'm on hotspot, so my Wi-Fi is super patchy. I thought the book referenced because I thought it could be different balances, but didn't the book say that with the same balance, a student, non-student, students less likely to default?
Yeah, that was their point. They were like, if you take just a random student versus like a random non-student, the student is actually more likely to default. And like the explanation is kind of like, well, they have higher balances, like they owe more money on average. So given the strong predictive effect of like owing money, and that students happen to, you know, owe more money, students are more likely to default overall. But if you take a student and a non-student and you give them the same balance, then the student is less likely to default. So yeah, like you're saying, Shirin, that's that's kind of like the interesting thing.
The same balance and income, because if it's just the balance, yeah, if it's just the same balance, wasn't it that the student was more likely? But if you add in the income, the student was less likely, I think.
Okay, yeah, I may have misread it. I think you're probably right, because I was trying to really blitz through the chapter. But I think the question still kind of holds. It's like, well, what's kind of happening there? I was just thinking like, well, presumably it's something like students have people that can bail them out, like more than non-students, and students have parents. So when they do get into like debt, they have other people that can pay their balance off more than people who are non-students. I don't think it really goes into the whys or anything in the book. So again, I might have missed it.
And maybe it depends on which country the data came from. Maybe in some country you have some student allowance, so the student is sure of his income, which somebody who is working could lose his job. So you don't. It depends which country.
Yeah, I think in the real world it certainly would. I haven't actually got the data set yet. I'm just taking this. This was all from the book.
And they've also chosen to go. I assume it's like college student. They've chosen to go to college, which I think, and at some level indicates some amount of responsibility.
It depends what you're studying.
Yeah. In general, obviously there's some other stuff that's not in your predictors that is maybe gonna like tell you or kind of explain what's happening. I did think before we go to the multinomial regression thing as well, like did people stop and dwell on like odds ratios and like the log of the odds ratios? Because I don't know if it's like too obvious or anything, but it's interesting to point out like that has a nice property, and they say kind of this in the book, is you center them at 0. So like if the coefficient is below 0, then it's like less likely to lead to a default. And if it's above 0, then it's more likely to lead to a default, which that property in general for like a more like logistic regression is a good motivator of why you would take the log of the odds ratios. Because if they don't point that out or you don't see that, then it seems like, well, why take the log? Why don't you just do something else? But it's to get that kind of property so that you can interpret the coefficients nicely.
Yeah, and that was where the student or not student switched. If that was the only predictor, it was a positive coefficient, and then once you added in 2 predictors and you had income, and it was a negative one. Yeah, it's interesting.
Yeah, they said actually, didn't they? They said like be wary of like making really simple models because you might interpret the results wrong. Yeah. I think that's all. I didn't take super loads of notes. I did code up the default probability just to look at what the formula looks like in Python. So and it's like, I feel like it's always a lot simpler in code than it is in the formula, at least if like you didn't do maths at uni or anything. So I will post that just in the channel.
Okay, I think.
And
Is there anything
because
about?
because he has been a long time, I know that something important about the logic is also used in economic about the utility. And it's also a way to see the, when you do some relative preference, and the logit function is also well used in when you do microeconomy. Sorry, the discussion. I forget, I forgot about that, but it's about the beta, the utility. I will try to dig. I will try to dig about that, but it's you have to understand that as a relative preference as well.
Oh yeah, that's like what an odds ratio kind of does, right? Like if you have like the odds of one thing and the odds of another, and like say you turn that into what someone prefers, then you can check like a preference against another preference. Like you check how in odds ratios, like what's the more likely event relative to the other one. You take the odds of one over the other. So I guess yeah, you're weighting preferences instead of odds at some point.
Is that related to this like default class, like the preference of it?
I think Sandrine was talking about a more general property,
Okay.
rather than this data set. What I like to do is I'm going to put flags in stuff. So when there's stuff that comes up that we can't resolve on the spot, I'll just drop like a flag in the chat and stuff so that they come back through.
The multinomial logistic regression is used when predicting a variable with more than two classes, and we need to select a class to serve as the baseline. But the interpretation of the coefficients has to be done with being tied to that choice of baseline. Or there's this like softmax coding, which it sounds like we're going to go more into in the resampling, I think is the next chapter. Okay, and then the generative models. Generative models for classification are modeling the distribution of the predictors separately for each of the response classes. And again, asking why not the thing we just talked about. Logistic regression won't work well when the parameter estimates for the logistic, when there's substantial separation between the two classes. And if the distribution of the predictors is approximately normal in each of the classes and the sample size is small, and just a plus is that most of these methods can be naturally extended to the case of more than two response classes. So there's just some common notation here I won't go into. And the three are the linear discriminant analysis, the quadratic discriminant analysis, and the naive Bayes methods. And I just put some notes here about the best situation to use each of these. Before I get into the empirical analysis of like the 6 scenarios, did anyone have any questions for the group about these classifiers or anything to discuss about these classifiers?
I wonder if we could come back a bit next week, if that's all right, because there's definitely some stuff in LDA and QDA that is like worth dwelling on, but I don't personally like know it well enough to talk about. But it probably is worth like 5 or 10 minutes or something next week to dig a bit deeper.
Okay.
Yeah, I would like that too. I definitely need to build some intuitions, I think, about both LDA and QDA. I need to like maybe understand the formulas a little bit better. So I'd love that also.
Yeah, one thing I would say is get the assumptions as well from like Wikipedia or whether or like a different book or anything. Because the assumptions and the difference in the assumptions between QDA and LDA kind of like elucidate, well, like why would you use one or the other? Like why do you have both? And like what do they actually do? I just don't feel like ready to talk about that in any level at the moment.
Yeah. It seemed like the main one to me was the covariance matrix being common across all the classes. But that's as far as I got with it.
Yeah,
Do we
and it's
wanna
in
do the-
QDA that it drops that assumption. Well, sorry,
Yeah.
let me not derail and go in.
Okay. Do we want to do the empirical comparison now then, or and maybe do the analytical next week? Cool. I put the screenshots here. They're kind of blurry, I think. Yeah, they're blurry. From the figures. So they have these 6 scenarios. 3 of them have like a linear based decision boundaries, and 3 are non-linear. So we'll start with the linear ones. They're all just slightly different. There's no like details about what the scenarios are, like not like real world practical details about them. But we can kind of guess why some of the methods worked better in some cases. So like scenario 1 had uncorrelated normal distribution predictors. So the LDA performed really well because that has a normal distribution assumption, and so on and so forth. Scenario 2, naive Bayes didn't work well because the predictors there's a correlation between predictors. Same with scenario 3 with the naive Bayes. Can you even read the like? Oh yeah, maybe you can read the like x-axis on there.
Yeah.
Okay. And scenario 3, I think the quadratic performed poorly because of the t distribution, they were not normal. That's why. And then for the non-linear, these are a little bit smaller, even. Scenario 4, so normal distribution, and has correlations, and the QDA performed quite well. Does anyone have any questions about why any of these, either like in the linear or non-linear, why any of these didn't perform well or did perform well?
Not so much a question, because I probably need to read it before I know enough to question it, but
Yeah.
interesting that certainly in the first 3, logistic regression kind of smashes it out of the park on all 3 of them. Like, yeah, for all the like fanciness of the other methods, like logistic regression just does well consistently.
Yeah.
I think even when we get to like trees and stuff, like I tend to find nearly always logistic regression basically does as well as everything else. Or is like always like second best. And yeah, well, it is just always seems like a very good model.
Yeah. Okay, we'll finish up the chapter there. So
even on like the non-linear ones, not awful.
yeah.
And then Poisson regression, I like don't know how to not say it with like, because isn't that like fish in French, I think? I like always hear it with a French accent in my head.
Yeah, Poisson is fish and Poisson rouge is pussycat, I think. If I remember like from school.
I assume it's like someone's last name or something. This is the last in the book. They discuss like the generative models I don't know, I couldn't figure out why they like specifically put the Poisson regression underneath the generative models. So I'm gonna go slightly a different order. Similarly to predicting the probability of qualitative variables, negative predictions of count data are not meaningful. And by count data, the example in the book is about the estimate of how many users of a bike share program in a city, different months of the year and different hours of the day. And so you can see it's like really low in January, February, highest in like the spring and the fall, and then drops during some of the warmer months of the year. And then is really low throughout the night, and highest during like commute hours. And then one issue with using, I think it's the linear regression, or maybe it's the logistic regression. No, it's linear, is that this count data violates the assumption of homoscedasticity. And so the mean goes up. The mean number of bikers increases, and the variance also increases. Yeah, that's right. And then the Poisson distribution, in a Poisson distribution, the variance is the same as the mean. And so that violation of the homoscedasticity is okay. So the larger the mean of y, the larger its variance, which we can see here in these charts. And in the Poisson regression model, rather than modeling the number of bikers as a Poisson distribution with like a fixed mean value of 5 for the whole model, we can vary it as a function of the covariance. So that's the Poisson regression. And then basically the generalized linear models is everything we've talked about so far, the linear, logistic, and Poisson regressions. They are all known as like a generalized linear model. Each of them uses predictors to predict a response. And that, so like this, any models that follow this recipe are called a generalized linear model. That was like the big reveal at the end of the generalized linear model section. Oh, and information of the Poisson distribution. That is the whole chapter. Any questions that we want to discuss? Sounds like for next week we can do, I was thinking some of the exercises. Maybe we could work through some of the exercises together. And then it sounds like we want to do some more discussion about the generative models.
Yeah, I think so, that sounds good. I think because as well in the bits in LDA and stuff, it gets into like a few of the metrics. Like it references sensitivity and specificity, but also like precision and recall. And they're also pretty good to like dip into, I think, for a small deep dive. Do you want me to keep the camera rolling? Are we going to discuss stuff, or shall I stop and then we have a small debrief after?
I don't have any specific discussion questions.
Okay, anybody, any takers? Okay, let me stop.